Today we discuss about the topic current electricity. In this chapter we are going to discuss about moving charges. The charges are under motion. In previous chapter, that is in electrostatics, you have studied about stationary charges, right? So here we are going to discuss about moving charges. Charges are under motion. We know conductors or metals are good conductors of electricity, right? That is, if you consider a conductor, there are a lot of free electrons in it. Copper wire or aluminum wire, that is metal wire, there are a lot of free electrons in it. In normal situations, see, these electrons are in random motion. So these electrons will be moving here and there. So that will not result any electric current, because for an electric current, there should be a unidirectional flow of charges. That is, the charge Q flows through this region like this. We consider a cross section of this. The intensity of the current intensity of the electric current, I, means the total amount of the charge flowing through any cross section of the conductor in unit time. That is, we can say that I equal to total amount of the charge Q by total time taken to flow through it. The total amount of the charge crossing any cross section of the conductor in unit time. That is what is called intensity of electric current. We know the unit of current is, so unit of charge is coulomb and time second. So the unit will be coulomb per second or ampere. Symbol A. That is, when charge flows through the cross section, any cross section of the conductor, the intensity of electric current is the total amount of the charge crossing any cross section of the conductor in unit time. The unit of electric current is coulomb per second or ampere, Q by T. So this is the average current or intensity, that is Q by T. So instantaneous current, we can say limit delta T tends to 0, delta Q by delta T. At any instance, the charge flowing through the cross section of the conductor will be limit delta T tends to 0, delta Q by delta T. Like in velocity and all, you have studied already, that is, the average velocity will be total displacement traveled by time, and instantaneous velocity will be delta S by limit delta T tends to 0, delta S by delta T. Like that small instant we are considering. The instantaneous current at any time T will be equal to limit delta T tends to 0, delta Q by delta T. So the intensity of electric current through the conductor will be the total amount of the charge flowing through the conductor in any cross section of the conductor in unit time. The total amount of the charge flowing in any cross section of the conductor in unit time. That is what is called intensity of the electric current. Now, if you consider a conductor, we know there are a lot of free electrons. Conductor means metals. We are talking about metals. So there are a lot of free electrons in it. These electrons are in random motion. That is, these electrons will be moving here and there. So that will not result any electric current, because there will not be any net crossing through the conductor. Net flow or unidirectional flow will not be there. Here electrons will be moving in this direction, one will be moving in this direction, here and there, like this. So the speed of this electron is called thermal speed or thermal velocity. The speed or this velocity depends on the temperature. So this will not result any net current, because electrons are not moving in a single direction. So for the flow of current, there should be a unidirectional flow. The charge should move in a single direction. Here there is no net crossing. That is, we consider a cross section here one electron will be moving in this direction, one will be moving in this direction, like this. So there is no net crossing. That is, in the presence of an electric field, we are not applying any cell at this point. Now, when a cell is connected at this point, V is the potential difference applied here. We know when a cell is connected here, this is positive sign, so positive, and this is negative. Now an electric field will develop in the conductor. Now what will happen? The electron will get accelerated in the opposite direction of the electric field, right? So electron will be accelerated in the opposite direction of the electric field. So the random motion will stop and they start moving in only in one direction like this. So here, I think this is A, this is B. Now electrons start moving from B to A. So in the presence of a potential difference or an electric field, the free electrons will move in a single direction. So this will result in electric current. So here electrons will be moving in this direction. Free electrons will be moving in this direction, that is in the opposite direction of the electric field. Okay. So while moving, what will happen? See, there are a lot of free electrons here, and while moving here, these electrons will collide with the lattice points. This collide with the other electrons and this collide with the lattice points. So what will happen? While moving, the electrons will get accelerated, but they collide with the lattice point. So the velocity of the electron will get reduced. Again, still there is an electric field here. Again, the speed will increase. Again, collide with the lattice point, speed will decrease. So the electron get drifted in this direction. That is, if you take this, these are the lattice points. So electron will have an acceleration between two collisions. Between these 2 points, their speed will decrease. Again, they get accelerated because there is an electric field throughout. Again, they get accelerated. So they accelerate. Again, velocity becomes 0 or decreases. Again, accelerates, increase, decrease, like that. The electrons will move. This average velocity with which an electron in a conductor gets drifted in the presence of an electric field, that is called drift velocity. We represent it by the symbol VD. So the drift velocity is the average velocity with which an electron in a conductor gets drifted in the presence of an electric field. Their motion, the electron's motion will be in the opposite direction of the electric field, right? So in the absence of the electric field, these electrons are in random motion. That speed is called thermal speed or thermal velocity. But in the presence of an electric field, these electrons will get drifted in the opposite direction of the electric field. And that motion will be only in one direction here. But the random motion will not result in electric current because that is moving here and there. There is no net crossing of electrons, right? Or net flow will not be there. Unidirectional flow will not be there. Here, these electrons are moving in a single direction. So that will result in electric current. And that velocity is called drift velocity. So we already said in a conductor, these electrons, in the presence of an electric field, these electrons get drifted while moving, they collide with the lattice points. So in between these two collisions, there is an acceleration. Again, while colliding, the speed will decrease. Again, they get accelerated. Again, decreases. Again, accelerated, like that. The electrons move like that. The electron interval between two successive collisions, that is called relaxation time. We represent it by letter tau, relaxation time. The time interval between two successive collisions, that is called relaxation time. Okay. Now, when an electric field applied, we know the force acting on a charged particle, F equal to QE, right? Here, F equal to EE. E is the charge of electron, minus sign. It is in the opposite direction of the electric field. So, F equal to minus EE. Now the acceleration of the charge. We know F equal to ma equal to minus ee. So a equal to minus ee by m. So this is expression for the acceleration of the electron in the presence of an electric field. Now the electron start moving from this point. When it reaches here, the time taken will be tau, that is the relaxation time. Assume that electrons start with zero velocity. Now the velocity, the final velocity of the electron will be v equal to, we can use the equation v equal to u plus at. That is 0 plus a is acceleration minus e by m, and the time is 2. So the expression for drift velocity is v equal to vd equal to minus e by m into tau. This is the expression for drift velocity, Vd equal to minus E by m into tau. Repeat. When in the presence of an electric field, the electrons start moving from this point to this point. Again, these are the lattice points. While moving, they get accelerated here and collide. While colliding, the speed will decrease. Again, they get accelerated. Again, decreases. Again, accelerated, like that. Electron move like that. Okay. Now, the force acting on the electron, force acting on any charge in the presence of electric field, we know F equal to QE, right? Here I took E is the charge of electron, so force equal to minus EE. The force is in the opposite direction of the electric field. The electron will move in the opposite direction of the electric field, so F equal to minus E. Now F equal to MA, so the acceleration will be minus EE by M. Now you know the time interval between these two, the collision between two collision is relaxation time tau. Now we use the equation v equal to u plus at. Starting velocity is 0 minus E by m into tau. So this velocity Vd is called the drift velocity minus E by m into tau. So the drift velocity, it is the average velocity with which an electron in a conductor gets drifted in the presence of an electric field. So this drift velocity will result in electric current, or due to this drift velocity, there will be a net unidirectional flow, or there will be a net current. So there will be a net current through the conductor only in the presence of an electric field, right? Mobility of charges, mobility of electrons. The ratio of the drift velocity to the electric field, the magnitude of the drift velocity to the electric field, that is called mobility. So modulus of Vd by E, that is Vd equal to E by m into 2 minus E by m, but the modulus will be E by m into 2 by E, that is E by m into 2. So this will be the expression for the drift velocity, E by m into tau, right? The ratio of the drift velocity to the electric field, that is called the mobility of the electron, or mobility of the charging areas. So for any charging areas, the mobility means velocity to the electric field. Okay. So here E by m into tau, that will be the expression for the drift velocity, or sorry, mobility. Now we need an expression for the intensity of the current and drift velocity. Relation between intensity of current I and drift velocity. Consider a conductor, metallic conductor of length L and area cross section A. A potential difference V is applied between the two ends. We know the intensity of the current means I equal to Q by T. Q is the total charge in it, right? Total charge flowing in unit time, crossing the conductor in unit time. Now, the total charge means the total number of electrons or total number of charge carriers into the charge of one electron. That will be the total charge, right? So total number of electrons into charge of one electron will give the total charge carriers. That is N into E by T. Where N is a total charge carriers number, total number of electrons in that conductor. So take N is the number of electrons per unit volume. Number of electrons per unit volume. Then N will be equal to N is the number of electrons per unit volume. N into volume, that is area into length. Area of cross section into length will be the volume of the conductor. N is the number of electrons per unit volume. So into volume will give the total number. So NaL into T by T. Okay, but L by T is the distance traveled by the charged particle or the electron in unit time. So L by T will be equal to the drift velocity. So we can write I equal to N E A V, where Vd will be equal to L by T. This Vd equal to L by T. That is distance traveled by the time taken will be the value of Vd, drift velocity. So I equal to N E A V. This is expression for the intensity of the current in terms of drift velocity. N number of electrons per unit volume, E charge of electron, A area cross section of the conductor, and Vd is the drift velocity. Okay. We know electrons will move in the opposite direction of the electric field, right? That is in this case negative to positive. This is positive side and this is negative side. Right, electrons will move in this direction. But conventionally we consider the current is in the direction of the motion of the positive charges. So when the electron move in this direction, the current direction will be in this way. That is high potential to low potential. That is a conventional current. Okay, current is always from high potential to low potential. In this case, this is high potential region, this is low potential region. See, the battery is positive terminal of the battery is connected to this end and negative terminal to this end. So high to low. This is the direction of the current flow. So high potential to low potential. So the electrons move in the opposite direction of the electric field, that is negative to positive. But the conventional current is from positive to negative. The opposite direction of the motion of electric field, electron, or the direction of the motion of the proton, we can say. Okay. Now we introduce the term current density. G. We already discussed about the current. Electric current means the total amount of the charge crossing any cross-section area of the conductor in unit time. That is what is electric current intensity I. So current density is the total current per unit area of cross-section of the conductor. That is, A is the area of cross-section. When a current I is flowing through it, current density J equal to I by A, current per unit area of cross-section. So current density is a vector quantity, but electric current is scalar quantity. Electric current is scalar, but current density J is vector. J will be a vector quantity. So I by A is unit is ampere per meter square. Okay. So in this case, actually, we have to consider the current. Here we took current flowing in this direction, and that is perpendicular to the area cross section we consider, right? So if we take an area like this, then this is A, this angle is theta, and current is flowing in this direction. Now this area will be A cos theta. right? Now the current flow is in this direction. The area perpendicular to the direction of the current flow will be A cos theta. Now current density in this case will be I by A cos theta. That is, current density is the ratio of the intensity of current to the area cross section or area perpendicular to the direction of the current flow. The current per unit area in a direction perpendicular to the current flow, or we can say, right, J equal to I by A perpendicular, meaning current per unit area in a direction perpendicular to the current flow, right? Here this current is already perpendicular to the area cross section, so we need to write J equal to I by A, right? And here in this case we took area inclined at an angle theta with the cross sectional side here. So the cross sectional area here will be, in terms of A, will be A cos theta. So J will be equal to I by A cos theta, or J equal to I by A perpendicular. A perpendicular means perpendicular to the area, perpendicular to the direction of the current flow. Current per unit area in a direction perpendicular to the current flow. That is what is current density, J. Current density J is a vector quantity, but electric current I is a scalar quantity. Okay. Now we can derive a relation between J and E, that is current density and electric field. J and E. We know J equal to I by A. I equal to N E A V D by A. That is J equal to N E V D. But we know V D equal to E E by M into tau. So equal to N E into E E by M into tau. So this becomes J equal to N E square tau by M into E. J equal to N E square tau by M into E, where N is a number density, E is the charge of electron, tau relaxation time, M mass of electron. So we can take these quantities N, E, tau and M as constant. Tau will be constant at a particular, depends on the temperature. On increase in temperature, tau relaxation time will decrease, but at a particular temperature, tau will be constant. So we can write J equal to, all these quantities are constant, so J equal to sigma E. So this is a relation connecting current density and electric field, where sigma equal to N E square tau by M. It is called the conductivity of the conductor. Sigma equal to conductivity. Sigma equal to N E square tau by M. That is called the conductivity of the conductor. Okay.